part actually customer part. So customer come to the actually resolving decks or what I can say token counter or some places. Okay, so we can say token counter or resolving decks, and every means resolving decks so have actually some throughput. Okay, and then customer go into the lobby, and once customer go into the lobby, then they go for processing. So this is the lobby. Okay, once they clear the means what I can say resolving part, then they go to lobby, and then next is a processing. So then their work get processed, and this part is processing. And how many counters are means what I peoples are there, and what is the tax per second? What is the performance of the processing capacity? So this is the processing capacity. So this is P peak. We say in this example there are 4 people, and at a time 4 tasks per second can be, or 4 tasks per unit time can be processed. In some sense, you can say. And in computer system, this kind of similar things also it happens. So this is actually customers. Okay, so getting data from actually what I can say external memory to the nearby places of processor. Then we have lobby. Okay, so ready to execute kind of things, and then it executes. So this is the how data is coming, and for each data how much computations we require, and then we process the data. So in processor also we have similar kind, in processing system also have similar kind of things. So if you look at, so resolving door throughput is BS, number of customer per second it is trying sending. When suppose they are verifying some identity card and something, and they are sending to lobby, and each customer have 2-3 taxes or some number of taxes per customer, and after that this taxes customer will go to the processing desk and they will process. Okay, there are clearly 3 things: BS, intensity. So intensity is a number of taxes per customer. I is intensity and number of taxes per customer, and then processing capability of the processing system, that is P peak, number of tasks processed per second. So clearly 3 things: customer per second, then tasks per customer, and then processing capability tasks per second. How many tasks per second get accomplished by the processing system? The similar things we'll see in the computer system. So how fast tasks can be processed? That is tasks per second, and the bottleneck can be either BS, this part. So maybe either this part. This is resolving decks. Okay, bottleneck can be either servicing desk, service decks, or resolving door. So service decks means if P peak is low, suppose resolving decks is sending more number of people, more number of amount of work, but processing is very slow, then that will be bottleneck. Service decks will be bottleneck. If resolving door is not sending many people, many taxes to processing decks, then resolving decks is actually bottleneck. So if you look at the things, so either one can be bottleneck. So either service decks or resolving door. And what you will get performance? Ultimately, performance will be minimum of P peak and IBS. So Joe, come here. So that will get output. So whether this IBS is small or P peak is small, whichever is small. So that will be the ultimate performance, not the higher one. Okay, so lower one will be performance. So, and this model is called roopline model. So we'll discuss the roopline model with examples. So high intensity, P is limited by execution. That means performance is limited by execution. Suppose there are many customer coming, okay, with many work, and there are not many service decks are available. That means the performance is limited by the service decks, or performance is limited by executions. Low intensity. Suppose there are many service decks are there, many worker are there, but they are not getting enough work. That means performance is limited by bottleneck. That is resolving decks bottleneck. So it depends upon means two scenarios. It depend upon both the things: service decks performance and resolving door performance. Okay. So roopline model says that whichever is the minimum is the final performance. If you plot the things, what will be? So what you can say, if you plot performance will be, if you plot the things.
Excuse me, sir.
Yeah.
So these customers per second is the customers request coming, or the customers that are allowed, like it can
Customer per
process.
second is number of customer coming from the resolving desk, or what you can say a reception desk.
Okay. So then, sir,
So how
if
many
there are
customer it is
less.
sent, and I is per customer how many works.
Okay.
Intensity.
Excuse me,
Okay.
sir. Sir,
Yeah.
I did not understand the analogy here. So, what exactly is the customers coming through the door?
So
In
customer is
terms of
a customer coming through a reception door, and reception just check the means what I can say it sends means looking at the what I can say some kind of features, it will send to the lobby. Just like whenever
no,
if you are
I
not
meant,
getting enough customer, you are not
no, I
getting enough
meant in terms of the computer. What is this analogous to? The customers
that I will
coming
see.
in. What?
So this is what I can say in terms of bank we are saying, but we will analyze to computer also. So suppose you require a lot of data processing, but you are not getting a lot of data. Okay.
Okay.
Suppose you require a lot of data processing for data, but you are not getting data. Then your resolving text, that is, you are not getting proper amount of data. That is the bottleneck, not the processing. And if you are able to get a lot of
And
data, but your processing power is less, then your processing power is the bottleneck. That we will see.
okay.
So high
Okay, fine, fine.
intensity. Okay. So high intensity P is limited by executions. Okay. Performance is limited by executions, and low intensity performance is limited by the bottleneck. So clearly, so if you plot the thing performance and if you with intensity, so intensity is I into BS. BS means number of customer entering or number of data entering, and per data how much computations you require. Okay, so this is how many customer entering and per customer how much tasks they require, and this one is actually this is I into BS. This is increasing. Suppose you increase the intensity, number of data increase and intensity you are increasing, but you have another limit is there, that is called means executions. Okay, even if you increase the number of customer, but the bank have suppose 4 counter or 5 counter. So 5 people, how many they can process? If you increase simply I into BS, it will not increase. So that will be limited by the number of service decks, number of counter ultimately. So in this processing system also, so how much it can process, it will be limited by that. Okay, so that is called, this is actually roopline. Okay, so this is roopline. So even if you increase the intensity or number of customer into bank, so it depends upon how many actually service decks are there. The performance will depend upon number of service decks. Okay, so if number of service decks is more and you are sending less, then it performance depend upon, so this is the performance. In this case, this is in this point, so number of customer is less, but number of service decks is more, they are more capable. But in this case, more number of means customer are there, but less number of servicing guys, particularly service decks are there. Then performance will be limited by the service decks. That means performance are limited by executions. This one is performance limited by executions, and this one limited by you are not getting enough customer. Okay, so this is standard roopline model. So is this clear? This is a very basic one, very optimistic and very simplistic model. So we want to find out why the bottleneck. This is common flow model. Suppose you have a pipeline, and pipeline there is a blockage. Then performance of pipeline will be depend upon the blockage. And if you look at the roopline model, so Pmax is the peak performance of max performance of the machines. Okay, so earlier we looked at the peak, P peak, and now instead of P peak, what we are trying to look at actually, if you look at P peak, so this is the P peak. P peak is means this point is P peak. Okay, so knee point is the peak performance of this system we will get. So not more than that, and P peak will be I into BS at per that point. Okay, so that is the best resources we can use. So Pmax, peak performance of the machines. I is computational intensity, work per byte transfer over the slowest data path utilized, the bottleneck. BS is the applicable peak bandwidth of the slowest data. Okay, this is for compute system. So compute system. Okay, so earlier that is bank system, now it is SAM compute system. Okay, Pmax or P peak. But ultimately performance will be minimum of either P peak, and then what is the intensity? That is F by B. What I was saying, F by B means number of floating point operations per byte. Intensity is now we're correlating to the machine, not the bank. Number of floating point operations per byte, F by B. And here is how much data you are getting from memory to processing system. That is byte per second. Okay, so byte per second. So in the BS means it is kind of, we can say clearly it is what? Bandwidth, available peak bandwidth of the slowest data path. So it is BS is bandwidth. So number of data coming, so amount of data coming per second, and this is amount of I is number of operations required per data per byte. Now we are able to correlate. Okay, so clearly the same number of customer and per customer how many tasks. Okay, so here bandwidth byte per second, and then per byte how much operations we require.
So, sir, it is the largest amount of operations that we can require for any data.
Yeah, not largest. It depends upon applications. It depends upon the. Suppose I'll give you example. Many examples I have. Okay, so based on that we can calculate the F by B. So there is intensity. How we can calculate from a code. Intensity you can calculate from a code. Okay.
Sir,
So,
it's written the slowest data path utilized.
yeah, slowest data path. So ultimately, so given a pipeline, so slowest data path it determines the bandwidth, overall bandwidth.
Excuse
So
me, sir.
not the fastest one. Suppose
Sir,
you are
could you
getting something from Google. Okay, suppose you are getting from Google, and you have connected to your mobile using 4G, okay, or 3G connections. Even if you are connecting to another places with high bandwidth, you will not get the speed because you have connected through mobile. So that is the slowest path. Are you getting a point?
Okay, sir.
Slowest path is always get bottleneck.
excuse me, sir?
Yeah.
So could you explain I again, the computational intensity?
So I means actually work per byte. Okay. So work per byte over the slowest data path. So how much work per byte will see? Suppose I'll give you very simplistic example. So we'll come back to this place. So suppose this is another example. Okay. So this is example with this is application property. So this is the for loop. For I is equal to 0, I less than is equal to n, I plus plus. What you are doing, s is equal to s plus ai into AIOD. And suppose you are using a double data structure. Okay, I mean all S and A are double type of data. Okay, double precision floating point. Then if you calculate how many floating point operations you require. So you require 8 byte data. So 8 byte data you need to get it, okay, to the processor. And then how many operations you are doing per data. So in this case, per AI, for IR iteration per AI, we need to get 8 byte of data. And how many operations we are doing? Floating point operations? We are getting 2 floating point operations. Okay. So here intensity is 2 floating point per 8 byte. That is 0.2 FB.
Okay, sir. Thank you. I got it.
This is clear. It depends upon the what kind of code you have. So from the code you can figure it what it will be intensity. Okay. So suppose you have a machine parameter. So one machine is machine parameter 1. So one machine has parameter 1. So P peak. P peak is equal to suppose 4 gigaflop per second. So this is the performance of machines. Performance can perform, and this is the bandwidth. So data coming to the machines. This is the data. So suppose data can come to the machines with bandwidth 10 gigabyte per second. Suppose data can come to the processing places. Where processing happens? In general, processor, in FU processing happens. In processor, in functional unit processing happens, and data comes from memory, then cache, then register, then FU. So this is a clearly hierarchy there. Suppose data is coming to the FU with bandwidth 10 gigabyte per second. Then what will be the performance? So clearly from this you can directly you can say what will be performance will be minimum of P peak and IBS. What is I? I you have already calculated 0.25 FB, 0.25 FB, and this is how much bandwidth we are supplying the data to the processing unit. How much bandwidth of data we are sending to the processing unit, and this is the what is the intensity. Intensity per data, how much work? Per byte, how much work it require? For this loop, for this per loop, this is the calculations. Okay, and suppose this machine can perform, if data is supplied at infinite bandwidth, then it can perform up to 4 gigaflop per seconds. Okay, so then ultimately what happens? So this will be minimum.
Hello.
It can process very high, but he's not getting data. If you look at this point, 2.5 gigaflop per second. Okay, this is the ultimately require computations we are sending, but this can perform very high. Ultimately, which one is bandwidth? Means bottleneck.
2.5 gigaflops per.
2.5 gigaflop per second is the band means bottleneck. Machine can perform very high, but we are not supplying data with proper intensity. That means we will get performance 2.5 gigaflop per second.
Sir.
You got my point? Is this clear?
Hello. Sir, can
Yeah.
you hear me?
Yeah.
Sir, while calculating intensity, 2f must be divided by 16 bytes because we are bringing S and AI both.
No, S is scalar. So scalar get mapped to, I mean, so in last class also we have discussed this thing. S is a scalar variable. Whenever S is scalar variable, it can map to a register. Only array
Oh,
variable
okay.
you need to consider. Okay.
All right, all right.
Okay. So this N is very large. S is constant number. So N is very large. S is constant number. Even if you look at, if you calculate in that way, then for I is equal to 0, I less than is equal to N, I plus plus. Here also we are doing computations. This is also computation. This is also comparison. But we don't care. This computation is anyhow. This is for every iterations. We need to do an increment. We need to do a comparison. We are not taking care of that. What is the actual computation? This floating point computations we are looking at. Double precision floating point.
Excuse me, sir.
Yeah.
Sir, P peak is a property of the hardware, right?
Yeah. This is a property of hardware.
How fast my processor is, and how
Yeah.
is
How fast
BS
my processor?
and how is
How fast
BS
my floating point processing system is inside processor?
okay? So and how is BS a machine parameter?
PS means how fast we are sending or getting back data from memory to the processing system.
The bandwidth you mean
Bandwidth.
the data bus connecting that memory to processor.
Yeah.
Okay. So
So
isn't
and
it
data
fixed
bus
that
can be increased by the memory hierarchy. Suppose if you want to put a memory hierarchy, then you can increase the amount of data can be sent to the processing place.
okay, okay, sir, that's fine. Thank you.
Okay. This is very simplistic formula. Okay.
Sir, sir, I have a doubt. Am I audible, sir?
Yeah, audible.
Yeah, sir. When we are measuring performance, we are measuring the performance of the hardware or the whole system on chip.
No. So whenever we are measuring performance, with some benchmark we measure.
Okay.
So we run some benchmark and measure. And if benchmark have some issues, so in this case, this benchmark have actually only 0.25 floating point operations per byte. Intensity is 0.25 floating point operations per byte works for these applications, for this code.
Sir,
Code is different. This
then
parameter will be different.
hello,
If you are
sir.
sending, suppose instead of only 2 operations, suppose you are doing many operations on AI, many floating point operations you are doing, then in that case, this intensity will be higher. Yeah, yeah.
Sir, then the performance will depend on application
Yeah.
because application is deciding the intensity.
Yeah. So look at, so here, if you look at, this is machine parameter. First two are machine parameter, and this one is application parameter. And performance depend upon both machine parameter and application properties, both the things.
Okay, so let's say we are having few machine. Let's say we're talking about one particular machine, but we're having different type of applications. So
Yeah.
the performance of machine application, then performance will depend on application only because we're
So
talking
we
about
can say
one
in this
machine.
case, performance of a particular applications on a particular machines. That will be better.
Okay.
Okay. So in
Sir,
roopline
I have a
model,
question.
clearly, yeah.
Sir, so in this previous formula in the P peak, if this should also actually depend on application also, because if I have, let's say, a for loop with floating point operation with lots of data dependencies, in that case, I may not be able to reach this peak performance also.
Yeah, that we'll see. So we'll see a lot of code and what will be the intensity that we'll discuss. Okay.
Excuse
So
me, sir.
yeah.
Sir, if okay, can you take to the previous slide?
Yeah.
Sir, if here suppose BS is very low and my machine is very capable, the P peak is very high, so my CPU will just stall, right? I mean, it will
CPU
just
will not get performance naturally.
okay. What if BS is too high and P peak is low? Then what will happen?
BS is too high
Too high, yes, sir.
and
P
P
peak
peak
is
is
low.
low.
Yes, flops per se, flops are low of my
Then
processor.
then P peak is actually bottleneck.
Okay, so my processor won't demand that much data. Is that the case?
No. Yeah, processor don't demand more. Because
Okay,
processor
although
is
my
not capable, processor will not demand, and then that will be the bottleneck.
okay, so my bus can send more data, but it's not sending more data because processor cannot handle that much data, right?
Cannot handle it.
Okay, that's fine. Thank you, sir.
So if you look at this roopline model, Pmax. So Pmax peak performance of a loop, assuming that data comes from L1 case, it is not necessarily P peak. So that whatever someone asked just now. So Pmax peak performance of a loop, assuming that data comes from L1 case, it is not necessarily P peak. Okay. And I is computational intensity, work per byte transferred, and code balance. So we are using another term that is called code balance. And code balance is actually reverse of actually intensity. So we can say in byte per flop. Okay, so both are actually same term. So whether you say computational intensity or code balance. Okay, but code balance, what we are saying is code balance is inverse of intensity. So flop per byte earlier we were saying, now we are saying byte per flop. Okay, so how many bytes we require to get data to perform one flop? Okay, one floating point operations. So this is I is F by B, but BC is reverse, B by F. Okay, so this is BS by BC. So both are same thing. And BS applicable peak bandwidth for slowest data path, whatever we have already discussed. So what we are modifying this? I with actually BC, code balance. And factor to be considered in roopline model. So bandwidth bound may be very simple. Accurate traffic calculations, write allocates, try to will do. That also we'll discuss. and practical not equal to theoretical bandwidth what we get, and we have a saturation effect, consider full circuit only. Core bound one may be complex, how to calculate the performance. Okay, so one thing is bandwidth bound. So bandwidth, and another thing is how much p peak or p max we are calculating. So how we can how to calculate p max? There is p peak or p max may be complex, and multiple bottlenecks, load and store, arithmetic, pipeline, SIMD, and in general, limit is linear in terms of number of cores. If you are taking for multi-core, okay, so number of cores, but it may be more complex. So how to calculate? Exactly, getting this number may not be very easy for core, but for bandwidth bound, it may be a little bit simpler. And if you look at the roopline model, so this is the graphical representation. So this is the PMAX come from code analysis with or without SIMD. Okay, and adding another AFUs. So if you look at general roopline model, first case, only one line we have shown. Only one line we have shown. But here we are showing many lines. Suppose one line is read-only memories. Another line is max memory bandwidth, then max L3 cache bandwidth. Okay, so whenever you increase means what I can say memory bandwidth, then performance will increase. Performance means gigaflop per second will increase, and then p peak. This is peak. This p peak. Suppose a processor don't have SIMD instructions, then peak will be much lower. Additional many APU, okay, then performance will be lower. With some additional FU, performance may a little bit increase. P peak will increase. If you have actually SIMD and additional functional unit, then P peak may be higher. Okay, so it depends upon processor. So if a processor have more advanced or improved, what I can say, functional units, or what I can say SIMD functional unit and advanced pipeline APUs, then performance will increase. Okay, so you'll get more performance. And similarly, we need to supply data to the processor with different memory hierarchy. Then only our performance will improve. So that's this roopline model have many peaks we are seeing. So multiple ceiling may apply, different bandwidth per data path, different inclination ceiling. So this is different inclination ceiling. So this one is different inclination ceiling, and different PMAX, different flat ceiling. This one is different flat ceiling. This is one flat ceiling. This is another flat ceiling, and this is another flat ceiling. It depends upon the how we are calculating. If your processor have AVX instructions or SIMD instructions, then it will be different. If it processor don't have that, then that will be different. Suppose Intel Celeron processor. So have you heard about Intel Celeron processor, Atom processor? Hello.
Sir,
On student side, have you heard about Intel Celeron processor and Intel Atom processor? APU, have you heard about APU? So AMD APU.
Yes, sir.
So Intel Celeron, AMD APU, and then Atom processor. So these are actually very small processor, and they don't have many advanced functional unit. Means particularly SSC, MMX, and then SIMD unit you will not get. AVX instruction will not get. But whenever you go towards core architecture, so particularly either Ryzen core or i3, i5, or i7 or GN core, you will get advanced, what I can say, functional unit in that processor. So if you have advanced functional unit in that processor, then you will get actually more number of P peak, flat P peak. Okay, so that is the basic difference between in i3 or i7. So many i5 processor and i7 processor both have actually same number of core, but internally they may have a different number of functional unit. So in terms of core they may be same, but in terms of functional unit and capability they may be different. So whatever we see i7 processor, suppose 8 core i7 processor and 8 core Xeon processor. Both costs are not same. Performance wise also not same. But we can say both are octa-core, but both octa-core are not same octa-core. Okay, so it depends upon whether this architecture have additional FU, advanced FU, AVX instruction or not, SIMD instruction are there, it support or not. It depends. Okay, so now I'll show you means something. So okay, so let me go for another example also. So this is another very interesting example. So apply roopline model to some Haswell core and Haswell core Intel core for triad code. So this is we are taking a particular architecture. Okay, so we are taking a particular architecture and we are trying to test the code, this triad code. And what is this triad code? So for I is equal to 0 to n, so AI is equal to BI plus CI into DI we are doing. So we are trying to access 4 array. 4 array, A array, B array, C array, D array. Okay. So if you look at application properties, so how many bytes we are actually accessing? A we are reading, okay, B you are reading, C you are reading, D you are reading, 4 ith element of array we are reading, and AI you are writing back also. At the AI we are writing, okay, that means we need to write back the data at AI. So that means 4 read access and 1 write access, and per double element. So what is the number of byte? 8 byte. Double is 8 byte. So total number of we can say iterations per iterations. So 40 byte we need to access. And how many operations we are doing? If you look at how many operations, only this is plus operations we are doing. This one is doing plus operations and then multiplication operations. 2 floating point operations per 40
Only
bytes.
3 reads and 1 write.
Yeah.
So we have only 3 reads and
Yes,
1
sir,
write
why?
here.
No, 3. But whenever AI, so we need to get into the processor cache places, then only we need to read and then only you can write it.
That's
So,
not necessary, right? We can always write without that block being in the cache.
look at in general what happens. We need to get into the in real system what happens. So if it is write not allocate, then it happens. But if it is write
Yes, sir.
allocate, then we need to get the data, read it, and then only you can write it. So are you getting a point?
Yes, sir.
Yeah, that's
So
why we require
in this
actually
case, it's
4 read plus 1
no
write.
allocate and and write through cache.
Yeah. So that's why we require actually 40 bytes data, and we need to read 32 byte and write 8 byte. Okay, so total 40 bytes we require byte transfer, data transfer, and here we have only 2, what I can say, floating point operations. So intensity will be 2 by 40, so it will be 0.5 FB. Is this number is clear or something different? 2 by 40, it will be, yeah.
Yes, sir, it's correct.
Yeah, this is fine. And suppose machine parameter. So this is the machine parameter. These are the machine parameter. This is the application property, and same formula I use. Okay, so in this case, still this one is very small because number of byte transfer required is higher, and floating point operations what we are doing is 2 operations. Okay, and what we are supplying data means number of operations to be performed at processor is actually 2.5 gigaflop per second, but our processor had capability of 12.27. It can process 12.27 gigaflop per second, but we are not sending data. Okay, we are not sending computations to processor to process. That means this is the means the bottleneck. So here, this is the bottleneck. And this particularly, this code, particularly this code is called triad code. And this triad code is mostly used to benchmark the memory system. This triad code is mostly used for benchmarking the memory system, how good your memory is. Okay, so how fast you are able to transfer the data to the processing. Okay, so triad code used for memory benchmarking. Is this clear?
Could you explain again why we are transferring 40 bytes of data instead of 32 bytes? Why do we need to read AI exactly?
Read AI means whenever you are trying to write at AI, first you need to get the value of AI, then only you can write.
But why is that necessary?
Look at, so anyhow, so in most of the processing system, RIGS processing system, so we cannot do the means we need to get into the means value. Suppose how these things will get transferred into machine instructions. Suppose what I am doing is, suppose AI is equal to 5, suppose I am doing. So what in general we do?
A load operation and store operation.
So this is writing to a positions, but in general, directly means we don't do. This will be a converted to a read and write, both read and write. Because we need to get into cache, then only you can do both the things.
Okay. Okay, so load will take 8 bytes and then store will take 8 bytes and then total 40 bytes will be taken.
That way.
Okay.
And sometimes what happens in RIGS architecture, reduced instruction set architecture, all the operations will perform in actually registered, not in memory. We cannot combine the things. Okay, so in that way, we need to read this thing. Okay.
Sir, why are we not considering parallelization in this case? Shouldn't we multiply I into BS by N because all the operations can happen simultaneously?
No, that will think separately. Okay, so that can be discussed separately. So this can be parallel, but suppose you unroll the things and do the things, but still after unrolling also, parallelizing also. Okay, so
Yes.
you need to, because you need to get the data from the higher places. Suppose instead of one I, so I and I plus one iterations you do parallelly, you are saying, but ultimately you need to get the data.
Yes, sir.
So in that case, 4 operations we are doing, and again 80 byte, but intensity is still same.
Okay, sir.
Okay, so now this code balance or intensity calculate. So for different kind of thing. So first one is this is first one calculation is a little bit wrong. So this is so 24 it should be, okay, not 2. So AI for I is equal to, this is copy case, AI is equal to BI. So in this case, 24 byte per 0 floating point operation. And this is we are not saying, not applicable code we are saying. We are not having in this because infinite it will go. And for this case, scale case, we have 24 byte per 1 floating point. This is 24 PF. This is code balance. Code balance is exactly inverse of intensity. Okay. Code balance and intensity both are opposite. Okay. We are calculating code balance, but it is intensity will be opposite. This is 24 byte 1 floating point operations. In this case, 1 floating point operation. And are you able to see in this case 32. So 32 byte per 1 floating point operations. So we need to get 32 byte and assign to processor, then only it can do 1 floating point operations. That means intensity will be much more lower. So these are the, yeah.
Sir, in the previous case, in the first one, why only 2 bytes?
No, that is 24. That is my mistake. So this one is not 2. So this should be 24. So that is my mistake. So by mistake it put 2. It cannot be. Okay.
Sir, in the second case, why is it 24 bytes and not 32 bytes?
Hmm?
Is S a constant here or?
Look at this one is reading. BI is reading.
Okay. And AI also reading. And then AI is writing.
Reading and writing.
Okay. And what about S?
S is scalar.
Just a
Scalar
constant, right?
value
Not.
it can put into register.
Okay. Okay. Thanks.
If you calculate like that, then why not I? Many times we are reading I. Many times we are writing I. So we are
Yes, sir.
looking at only floating point operation or floating point vector operations. Okay, so AI, BI we are looking at vector operations, and scalar things actually goes into register. Scalar value S will goes to register. Is this fine? So this is another examples. Lot of examples. So this code is looks very nice. S is equal to S into AI square. So we have 4 byte we are getting, only reading, no writing, and 2 floating point operations. So this is 2 BF. This looks very nice.
Sir, we change the size of a floating point from 8 byte to 4 byte.
In this case, yeah, if it is float, then this is for float. I think so. Float, how many it will be? 4 byte.
And the last one was for double. Okay.
Yeah. For double, it is different. For float, it is different. This is again, this will be 8 into 3. This is for double. These are for float. So it depends upon float or double. Okay. So and how many operations you are doing. Is this clear? This is very simplistic examples. And if you look at memory analysis of any simple triad code, and what is triad code? So that I have already shown you the triad code. So this one is triad code. So AI is equal to BI plus CI into DI. So in this case, how many memory we require? Suppose all are double. This is in this case float. Okay, float also fine. Float case, how many bytes we require? 5 into 4.
220.
20 byte you require. And how many operations?
2.
So this is 1 operations and 2 operations. 2 operations. 2F. 2F per 20 byte. This is if you look at intensity. 2F per 20 byte. And this is 1F per means 1 by 10. So 0.1. 0.1 F per B. And this is actually a very typical code. So this is a streaming benchmark. Why we call streaming benchmark? We don't reuse. This is simple streaming benchmark. We don't reuse the data. So ith iterations data don't get used in jth iterations. Okay. So I plus 1 iteration or I plus 1, I plus 2 iterations. This is a streaming benchmark. We can think of it as Swiss Army knife for micro benchmarking. So suppose you want to report performance for different n. Suppose n is very large. Okay. So choose some iteration, n iteration. Suppose n is equal to n iter. So this n iter is suppose you make it 100. Make it 100. And accurate time measurement is possible. So we can run this code. This is very simplistic code. So what we are doing, we are declaring A, B, C, D, N, and then for 100 iterations. So we are running this code, and you are putting this very simplistic I is greater than n. So dummy something. This prevents Smarty Pants compiler for doing clever stuff. So sometimes what happens, if you are not doing any input output, then compiler simply remove the code and make it actually what I can say redundant code. suppose you are not taking input and output from the functions or something, then compiler will simply ignore the whole what I can say code. So to make the system so that it will not do the unnecessary compiler optimizations except the required, so we are putting this code. Okay, so if you don't put, then compiler will do some optimizations and it will remove the code itself because you are not using the code. If you are not using the code, okay, so for that purpose you are putting the dummy function call. And this kernel is limited by data transfer performance and all memory level on current architecture. Suppose you run this code on some machines, then you will get to know what will be the actually performance at different memory level. So what I am showing code is this one. This figure is like this. So suppose you compile the same code with ABX or without ABX. Suppose with ABX we are compiling. That means we are using minus O3 options. Then you will get performance, higher performance. Suppose n is equal to small, not loop length. This is n. The size of the data. N is equal to small. Then the data will fit into the cache. Okay, this is L1 cache. This is L1 cache. Data will fit into L1 cache, and you will get huge performance. Performance will get higher. Okay, and if you are not using O3 options, simple GCC compilation, then anyhow will not get performance because you are not using ABX options. Then performance will be very less, about 3000 megaflop per second. But if you are using ABX, then you will get around 7000 megaflop per second. And if n is smaller, then it will fit into the L2 case, L1 case. If n is little bit higher, then it will not fit into L1 case. Your performance will depend upon the size of the L2 cache, because now L2 cache is the bottleneck. You are not getting data from the L1, you are getting data from the L2 cache. That means performance is getting down. Okay, and again performance will be limited by L3 cache, then memory. So this kind of behavior you will see. So ultimately what if the size of the n is higher, then it need to come from memory, then L3 cache, then L2 cache, then L1 cache. Ultimately L1 cache supply. If the data feed into the L1 cache, then you will get the maximum performance. Is this fine?
Sir, what is the difference between AVX and scalar processor?
So AVX and scalar means you are not compiling with O3s. Most of the Intel processor and AMD processor, particularly core processor, i3, i5 or i7 or Xeon processor, they support advanced vector instructions. Okay, AVX instructions. If you compile your code with AVX for minus O3, then it will generate AVX instruction and it will run on means using that AVX instruction, you will get higher performance. Okay, so on that kind of processor.
Sir,
If you
then
don't
why
use
scalar processor, that L1 cache, there is no rise in performance for L1 and
because
L2?
whenever using AVX, then in general 64 or means 32 operations we are doing in parallel. That's why performance is higher. Because your P peak, if you are using AVX instructions, then your P peak is higher. Capability of processor is higher.
Okay, got it.
Are you getting your point? And if you
Yes,
are
sir.
not
So
using
this performance is that peak performance, it's not that minimum performance, it's the peak performance. Okay. Thank you, sir.
So if you are not using that minus O3 options, only you are using scalar computations, then you will not get that performance.
Yes, sir, got it.
You got my point? And because of that thing, if it is fit into L1 case, suppose it data fit into L1 case, you will get performance. It depend upon the whatever your AVX instructions is giving. Okay, if it is not fitting, then it depend upon the L2 bandwidth, L3 bandwidth, then memory bandwidth. And memory bandwidth is always slower. Memory bandwidth will be always slower. That means performance will depend upon memory. If n is very large, okay, suppose n is very large, then you can see performance is getting from. So this code, let me show you in the computer maybe. So directly. To see the
excuse me, sir.
yeah.
Yeah, in the previous graph, you wanted like the goal of the graph was that if the memory is like if the memory bandwidth is low, then improving the instruction architecture will actually like improving the performance will happen, or like
So
improving the
will not
performance
get
will happen when
will
on
not get performance. Suppose n is very large, so your data size is very large. Then what happens? It will not fit into cache. You will not get performance. It will be limited by memory bandwidth.
okay, and when the data is less, then we can actually improve by optimizing.
Okay.
So
So that's
for
why
high
if
data
you do a data
optimization,
optimizations, data access optimizations, then you can send your data to the processor very quickly. If you can send the data to the processor very quickly and your processor have capability to process, then you will get maximum. You got my point?
Yeah, I got your point, but then for like high data, when the bandwidth of data is high, then optimization doesn't matter. That means
I'm not getting your question. When
like when
bandwidth of
the data requirement is high for a program, then the optimizations applied to the program won't matter.
In this case, what we are trying to measure is how much the processing capability of processor, how much you are supplying. If your supply is higher and processing capability is also higher, then you will get higher performance. Any one of the things is lower, then you will not get performance. Meaning,
But then for AVX and scalar, like as you said that we can use AVX only when we are using O3 optimization. So
if
that
O3 optimization, then
optimization
it
will not.
uses AVX.
Oh, okay. Like that optimization uses AVX if AVX is available. Then suppose for high data availability, like when I am doing a program for like very high data, which requires high data throughput. So in that program, even if I apply like very good optimization also, it won't matter because the data requirement is high.
If data requirement is high, then it need to send from memory to the cache. Okay, so if you can use some kind of very good data access pattern, data access optimizations. Suppose you use very nice data access optimization and send the data to the processing element very nicely, quickly, then your performance will increase.
So then we will have to optimize the data performance.
Data access.
Data access. Okay.
Yeah. Ultimately, we need to. Ultimately, performance is limited by not by the performance of the actual processing system, but it is limited by the memory. Clearly, you can see this figure. So here, if data is small, then it depends upon means AVX performance. If data is bigger, then it depends upon the L2 performance, L3 performance, and memory performance. It depends upon the memory bandwidth ultimately.
Okay, sir. Okay, sir. Got it.
Okay. So if you can send the data from memory to the means L1 cache and to the processor very quickly using some data access optimizations, then your performance will improve.
Okay, sir. Okay.
Okay. So this is the code. So what is the time now?
Sir,
So
we have a class at 4. So can we?
yeah. So we can stop. This is the code, but okay. So next class we'll see again maybe.
Thank you, sir.
Excuse me, sir.
Yeah.
If my data type is float and I'm multiplying suppose two variables who are float and then I'm multiplying suppose two data, so two variables which are of the type double, they both require a single floating point operation.
No,
Right?
no, I'm not getting a question. Plus tell the question clearly.
I am multiplying two floats. Okay.
Two floats.
So how many floating point operations does this require?
Multiply two float number.
Yes. Just A and B.
Only one floating point operation is required because only one multiplication.
Yeah, and what if A and B are of the type double rather than float?
So that is also with a floating point operations only, one operations.
But
so in this case, we are saying one operations, both floating point operations and this operation is one operations. But we can categorize as when instead of flops, okay, M flops, we can say mega double precision floating point operations, we say, in case of
Oh,
double data.
okay. Yes, I was wondering because this is not like they both will take different number of cycles in
So
multiplication,
whenever you
right?
say float, whenever you say float, na, float means by default single precision floating point, single precision floating point. And whenever you say double, actually double precision floating point. Both are floating point operations.
Okay.
But this one is 32-bit and this one is 64-bit.
Okay. So this requires
And
more
whenever you
CPU
compare
cycles.
performance, we say whether it is flops in terms of single precisions or double precisions.
Okay. Okay, sir. Fine. Thank you.
So in the case I divide two floating point numbers, does it still requires one floating point operation?
So in terms of operations, we say one operations, even if it divide.
So in the formula, we would
Mhm.
use one floating point operation.
Which formula?
In case we are dividing two floating point numbers.
Dividing two floating point number means it is a, in that case also we say one flops, floating point operations.
All right, sir.
This is fine. Any other questions?
I have one more doubt, sir.
Yeah.
Suppose there is a code and there is a program which is first we are computing that program serially, we are providing the data also, but the data requirement is high. Suppose very large data requirement, 10 to the power 6 or more, and that program is serially executed. Then the uh, bottleneck for that program is the data. The data is very high, so that's why the bottleneck is data. So even if we parallelize that program, we use multiple threads to process the same thing, then also the performance will be same.
No, performance will be some. It will, if it is data is higher, then it will depend upon the memory performance.
So
When it is
parallelization
parallel program,
won't
it
work
depends
for that.
upon the memory performance.
Okay, so then also parallelization won't matter in that case also.
Parallelisms won't make sense. But suppose if your code have, that's why this is streaming benchmark. Whatever I told, this one is streaming benchmark. So in this case, so all data access, ith, bi, ci, and di, so they are accessing once, and they are after means next iterations I plus 1, they are not getting accessed.
Yes, sir.
bi, ci, and di, even ai, they are getting access on ith iterations. In I plus 1, they are not getting access. That means this is streaming benchmark. Only once it is getting access. After that, that means it will not take benefit from the cache. Okay. If you are running multiple times, suppose j iter, so in this case j iterations, whatever you are doing j iterations, if it fit all the array fit into this thing, then in the next iterations it can take benefit.
Sir, suppose one more doubt is that suppose we are performing matrix multiplication. Suppose we are performing matrix multiplication on large matrix, and then we want to parallelize the data and increase the performance. So we will do separately, we will allocate a thread to do one part of the matrix.
No. How to do data access optimization? Look at hello. How to do data access optimizations in matrix multiplications, that we'll see in the next class. Next class we have a topic. Okay.
Okay, sir.
So we have that thing. So don't worry. So we have how to improve the data access pattern for matrix multiplication and how to increase the data access rate. Okay. So that we'll see in the next class. We have how to do data access optimization for matrix multiplication. That we'll see.
Okay, sir. Okay.
In the next class we have. But for serial code, for parallel code, how we'll do that is different. So we'll see for serial code how to do data access optimizations. We'll do. And matrix multiplication is one of the best example we will see in the next class, tomorrow class. Any other questions or doubt? Okay, so if you don't have any doubt, then we can leave. So, and if you want to see, just let me show you the sum code. So this is actually with GCC -3 options. If you can see XMMS 0, XMM 0, XMM 1, these are actually vector register. This is SIMD code. Okay, and if you do without optimizations, assembly code without optimizations, you will not see that MMX1. MMX still you are getting, but will not get properly. Vectorized code will get. No, there is some issues. I'll sort it out. So you can see the how this assembly code is generated. And those who are here still, those who are here, you can see. So with and without optimizations, how this performance get difference. Are you able to see this thing? So for 1000 case, we are getting performance 125. After that, 30, 31. Slowly fluctuations are there. But in this case, we are getting this is O3 optimizations. We are getting performance 153. It should not increase, but because of some minor, what I can say, unpredictable thing, it is increasing. But we need to go for very high amount of that, then only we can see. This test, whatever they did, actually very old processor. Nowadays, processor changes, we need to change the data set completely. Then n need to be changed to very high, then only we'll get the actual thing, I think so. But we will see with optimization or without optimization, still there is a significant 30 and 155 time difference we are getting. So thank you. Next class we'll have actually data access optimizations, particularly matrix multiplications, how we can improve the data access and how to do very quickly, and these things we'll discuss. And then one class will be reserved for only what I can say pthread, means thread programming, one class for OpenMP, one class for MPA programming. So after that, the basic of actually HPC will be covered. Then we'll move towards our main scheduling and cloud and IoT business. So 1/4 of the class is for regular HPC. Okay, thank you.